Before Hubble, before James Webb, before any of the space telescopes we talk about today, there was a satellite most people have never even heard of. It launched in the pre-dawn darkness of December 1968, just 3 weeks before humans would first orbit the moon, carrying the most ambitious unpiloted payload NASA had ever attempted at the time. Formerly called OAO-2 the Orbiting Astronomical Observatory 2, it was nicknamed Stargazer, and it became NASA's first successful cosmic explorer, the first mission to prove that a working orbital telescope could actually deliver real astronomy. Without it, there's a real argument that Hubble never happens the way it did. So today, we're going back to where it all started, the mission that proved humanity could put a working telescope above the atmosphere and actually make it work. Let's get into it. Before we get to Stargazer itself, it's worth asking an obvious question. Why put a telescope in space in the first place? Ground-based observatories had already been producing incredible science for centuries. The answer comes down to one major obstacle: Earth's atmosphere. Our atmosphere is great for keeping us alive, but it's genuinely terrible for astronomy. It blurs incoming starlight, which is why stars appear to twinkle. And more importantly, it completely blocks large portions of the light spectrum from ever reaching the ground, especially ultraviolet light, which gets absorbed high in the atmosphere before it ever reaches a telescope on Earth. That meant an entire category of cosmic information, the ultraviolet signatures of stars, gas, and other objects, was essentially invisible to every ground-based observatory on the planet. If you wanted to see it, you had exactly one option: get above the atmosphere entirely. That idea had been discussed since the 1940s, but actually building a working, steerable, scientifically useful telescope, launching it into orbit, and controlling it remotely from the ground, nobody had proven that was truly possible. Not yet. NASA's answer was a program called the Orbiting Astronomical Observatory, or OAO, a series of satellites designed specifically to test whether orbital astronomy could actually work. The first attempt, OAO-1, launched in April 1966. It was a technological first step, but a power system failure shortly after launch left it unable to complete its science mission. It was a setback, but not the end of the program. NASA regrouped, refined the design, and prepared a second attempt, one that would carry 2 complete sets of scientific instruments and, crucially, actually work. At 3:40 a.m. Eastern Time on Saturday, December 7, 1968, an Atlas Centaur rocket lifted off from Cape Canaveral, carrying NASA's heaviest and most ambitious unpiloted satellite built up to that point. Formerly named OAO-2 and nicknamed Stargazer, it carried 2 separate instrument packages positioned to look out of opposite ends of the spacecraft. One was a cluster of photometers and spectrometers called the Wisconsin Experiment Package. The other was a set of ultraviolet detectors known as Telescope, built by the Smithsonian Astrophysical Observatory. 6 small star trackers helped the spacecraft lock onto guide stars, allowing it to be precisely steered and controlled from the ground, a genuinely difficult engineering challenge at the time, and one of the mission's most important technological achievements in its own right. For context, this launch happened just 3 weeks before Apollo 8 would carry the first humans around the moon. Space exploration in December 1968 was operating on multiple fronts at once, and Stargazer's success was about to become one of the quieter but foundational achievements of that era. Unlike its predecessor, OAO-2 worked, and it worked for years. Over the course of its mission, Stargazer provided the first orbital observations of stars in ultraviolet light, a part of the spectrum that ground-based telescopes simply could not access. Telescope alone recorded roughly 8,500 ultraviolet images covering about 10% of the sky, while the mission's experiments together produced nearly 23,000 measurements. Researchers eventually used the telescope data to publish a catalog documenting 5,068 ultraviolet stars. The mission also studied comets, providing valuable ultraviolet data unavailable from any ground-based observatory, and delivered detailed ultraviolet measurements on more than 1,000 individual stars. Not everything went perfectly. Some instruments experienced gradual sensitivity loss over time, and one calibration source became stuck, limiting data from part of the instrument suite. But overall, the mission far exceeded expectations, and Stargazer remained operational until it was finally shut down in February 1973 years longer than its original planned mission. Here's why Stargazer deserves far more recognition than it usually gets. It proved the entire concept of orbital astronomy actually worked. Before OAO-2, putting a functional, steerable, scientifically productive telescope into orbit was a largely unproven idea. After OAO-2, it was demonstrated fact. That distinction mattered enormously for everything that came after it. OAO-2 became the direct technological and institutional ancestor of a long line of space observatories that followed, including OAO-3, known as Copernicus, launched in 1972 and eventually leading toward missions like the Hubble Space Telescope and later instruments like Chandra, Swift, Kepler, Galax, and Fuse. Each of these missions built on lessons learned from Stargazer's design, its instruments, and its remote control operations. In a very real sense, every dazzling image that Hubble or James Webb has ever produced traces its lineage back to a satellite most people have never heard of. Launched in the dark hours of a December morning in 1968, 3 weeks before humans first left Earth's orbit entirely. It's worth sitting with just how different space astronomy was before this mission. For all of human history up to that point, every single observation of the universe had been filtered through Earth's atmosphere, blurred, incomplete, and missing entire categories of light. OAO-2 was the moment that limitation was finally broken, even if only in a modest early way compared to what came later. And this wasn't a flashy, headline-grabbing mission at the time. It didn't carry astronauts. It wasn't racing anyone to the moon. It was a quiet, technical proof of concept, the unglamorous kind of mission that rarely gets remembered, but without which the more famous missions simply couldn't have happened. That's often how major scientific progress actually works. Not with one dramatic leap, but with a foundational, less celebrated step that makes everything afterward possible. So the next time you see a stunning image from the James Webb Space Telescope, or marvel at one of Hubble's iconic deep field photos, remember where that entire lineage actually begins. A satellite named Stargazer, launched in the pre-dawn cold of December 1968, proving for the first time that humanity really could put a working eye above the sky. It wasn't the most famous space telescope, but it was the first one that worked, and everything since has been built on that foundation. If you want to keep exploring the hidden history behind modern space science, hit subscribe to Deep Space Files, because sometimes the most important missions are the ones nobody remembers.